much for invitation and opportunity to talk about our works on ion atom systems. So I hope that with my talk I will somehow convince you maybe that the mixtures of single ion with atoms can be very interesting new setups for studying anything between two-body and many-body physics. So most of my talk will be about two-body physics, approaching few-body physics, and hopefully soon also many-body physics in close collaboration with experimental groups. So first, I will maybe mention a few words about ultra-cold or cold ion atom systems, ion atom mixtures. So everyone here, I think, or most of you already heard about, everyone here heard about ultra-cold atoms, and I think most of you are excited about ultra-cold atoms and things that we can do with them. So, but comparing the ultra-cold atomic systems with ultra-cold ionic system, there are some differences. So with atoms, typically you can have large number of atoms, what is maybe far away from few-body physics, but of course you can reduce it to few atoms as well. But in general, you can have really large number of atoms. You can have relatively long coherence times. The systems are also fully controllable, and really this is fully quantum matter. On the other hand, trap ions are a bit different. So because Coulomb interaction is very strong, so typically we will have smaller number of ions because they will form Coulomb crystals once trapped. So the number of ions will be between few to maybe at most 100 well controlled. But we will work mostly with the single ion. And this is also like the kind of different aspects that already at the beginning of this experiment was very easy to trap and manipulate single particle, single ion, and have also the full information about its quantum state. I mean, these systems are strongly interacting. They are also fully controllable. And there are some differences. So for example, like with neutral atoms, you can naturally introduce the bosonic fermionic statistics. It's much harder with trapped ions. So usually when you make some quantum simulators where you want to have many-body dynamics involving fermionic or bosonic statistics, it's not based on the natural fermionic and bosonic nature of the ions, but somehow engineered additionally at the top of this kind of systems. And then already 20 years ago, probably people started thinking about combining this kind of systems, and first experiments are more than 10 years old, where the single ion or few ions were immersed into ultra-cold gas. And the idea was, again, that maybe by combining these two a bit different systems, the best of two worlds can be achieved, and some new emerging features can happen. Unfortunately, there were, or fortunately, because it was more challenging, so more work needed to be done. There were some problems to be ultra cold or in the quantum regime from the beginning. So typically, if you take your quantum systems of cold atoms, ultra cold atoms, your quantum systems of trapped ions, and combine them together, the coupling between the two subsystems will be not quantum because of a few reasons, right? So there is the mismatch that somehow taking two very well controlled systems behaving fully quantum mechanically, their combination, the coupling between them will be not. And there are a few reasons. I mean, one of the reasons is that energy scales are a bit different. Typically, the trapping frequencies for the ion are much higher. This is not maybe the most important. Then the second is that the ion atom interaction is a bit longer range interaction potential, and this naturally puts some kind of characteristic energy scales a bit lower. So it means to be in the S-wave regime, you have to go to lower temperatures. And the most importantly, probably, is that there is micromotion. So I will mention in a moment about micromotion in the pole trap, because you cannot have a static trap for charged particles because it's impossible to generate maximum or minimum of the static electric field. So always you have to add some time-dependent field, and this time-dependent field will induce the micromotion, and this micromotion makes lots of problems, also imposing the limits how cold your ion atom mixtures can be. So, and then of course there were already since for the last 20 years, people were looking for different possible applications. So from my perspective, as a partially chemist. I mean, the application in cold chemistry, what Johannes investigated intensively, for example, are very interesting. I mean, there are some proposals for doing some precision measurements. I mean, there are extensions of and questions asked what properties we can expect, for example, for ionic polarons or so on. I mean, also the systems can be, for example, maybe better for some application in quantum simulation. Like you can imagine, for example, like having very heavy ytterbium ions as your cores, light fermionic lithium around, and somehow this kind of system seems naturally to be much closer to electrons in the solid state because there is charged core, the range of the interaction is a bit longer, fermions around are light, so maybe not much difference between simulating solid state with mixture of potassium and medium, but somehow. Right? I mean, there were also some proposals, for example, to use the cold atoms surrounding the trapped ions as a cooler for quantum computers and so on. But of course, there were many different proposals, but it's still very challenging to go to the temperatures where the coupling between the neutral and ionic subsystems would be quantum. Right? From my perspective, also, it's a very interesting system because really lots of understanding of the short range of the quantum. Let's say quantum chemical nature of the short range physics is needed. Because typically when we have combination of ions and atoms that can be trapped, there will be charge transfer possible. So it means that the ground state, the combination of the ground state of two subsystems typically will be an excited state, electronic excited state of the combination, and then charge transfer processes can happen. And this can, for example, be a problem because this charge transfer can induce losses in the system and you can lose your ion before you do any useful application. Then, of course, to have all this or most of this application, you want to control the ion-atom interaction strength. You want to have, for example, Feshbach resonances that are typically used for neutral atoms. But to do this, you have really go to the S-wave regime. You have to go to the collision regime where you have just few partial waves contributing, but there are the temperature limit due to the micromotion in the pole trap. Right, so now going back to the micromotion, so to be sure that we know where we are, right? So if we put our ion in the trap, in the pole trap, where we have the static electric field plus some admixture of time-dependent field, then we can see that there is some secular motion of the ion, right? So this would be just the motion as of the particle in the harmonic trap, but then at the top of the secular motion, there is this small micromotion of the frequency of this time-dependent field closing the trap. And unfortunately, and once this micromotion is not a problem for application of ions on their own, if we combine it with the atoms, it can happen that depending on the parameters of the trap and depending on the parameters of the ion and atom, it can happen that there is in fact no even at all possible to cool hot ion with cold atoms, right? If we have standard conservative trap, if we put something hot and surrounded by something cold, we should expect that there will be some thermalization and we will go, I mean, the hotter particle will go to lower temperatures. With ion atom mixtures, it's not guaranteed, right? And there are some lowest temperatures, somehow threshold, which you cannot go below. So you can, for example, but there were lots of studies on this and people predicted that, for example, if you take very heavy ion and very light atoms, what is not maybe the best combination for efficient cooling, but it's the best combination to avoid problems with the micromotion or micromotion heating, because then this can be favorable. But for some systems, if you, for example, would have heavy atoms and light ions or particles of a similar mass, it can happen, heavy ones, it can happen that the micromotion limit can be as high as hundreds of microkelvins. What is lots of in our collision energy scale, right? So now you can look on the experimental realization. So there were lots of experimental groups, of course, with Johannes here as one of the leaders. And this is somehow the picture showing the different combination of ions and atoms that were studied, let's say, more or less before 2018. And here, this left bar of this plot shows the lowest temperatures that were actually at the time in experiments. And at the same time, I plotted these vertical lines that shows the height of the P-wave barrier for ion-atom collision, right? Because why it's important? Because as I mentioned, to have possibility to control the system with the Feshbach resonances, to see really the quantum effects the quantum coupling between two subsystems, we should be at least as cold as the height of the P-wave barrier, right? So for the 1/r to 4 potential, this is the potential for ion atom interaction, we can define the very similar thing as the van der Waals length, but now the generalization of the van der Waals length for 1/r to 4 potential, and somehow energy of this, and we can also define this will be the height of the P-wave barrier, and we can, for example, and I will be telling about quantum regime of collision, not S-wave regime of collision, when collision energy will be more or less of this P-wave barrier height. And as you can see here, for some systems, the gap between the temperatures in the experiments that were at around 1 millikelvin versus the lowest, versus the P-wave barrier were huge, like 6 orders of magnitude, because you can see here that because of the long-range nature of this ion atom potential, the characteristic length scale is typically order of magnitude larger than for van der Waals system, and the characteristic energy scale will be 2 orders of magnitude smaller, right? So it means that we have, on average, to be 2 orders of magnitude colder than for neutral atoms to be in the S-wave regime of ion atom collisions, right? So this was the challenge. But there are some systems where the gap was much smaller. So for example, if you have very light particle involved, right? So for example, with lithium atoms, because lithium is very light, the reduced mass is small, and this kind of characteristic energy is much higher. And at the same time, for example, if you see that we have lithium neutral atoms with some heavy ion, this is exactly the condition that we need for minimizing the problems with the micromotion. So luckily, we can have at the same time relatively small gap to go into the S-wave quantum regime with combinations of heavy ions with light atoms, and this also is favorable for the micromotion. So in fact, if we would add here the limits imposed by the micromotion heating, you would see that for the heavy combinations of equal mass combinations, typically the micromotion limit would be at higher temperature than this S-wave quantum regime. So it means that in this kind of experiments with the pole trap, you can never, if we don't find some tricks, you cannot reach really this temperature. But for systems of this heavy light mixtures, it's the micromotion limit would be much below. Okay, and as I mentioned, one of these favorable systems is the mixture of ytterbium and lithium atoms, ytterbium ion and lithium atoms, and somehow motivated by our experimental colleagues then in Amsterdam, already at the end of my PhD, we started doing some ab initio electronic structure calculations to understand better what's going on in the system. So as I mentioned already, because typically for ion atom systems, we will be in the excited state at the asymptote where we have collisions. So it means when ytterbium ion collides with the lithium, it's excited state, so the charge transfer can happen. And this was one of the first questions that our experimental colleague asked, if this process will be fast or maybe negligible. Because if it would be fast, there will be no time to do any useful physics. So we did the calculation, and luckily for this system, we found that these non-radiative processes, radiative processes or any lossless processes are very, very slow for several reasons. For example, because this entrance channel is quite well separated from the excited states and ground state, and at the same time, the energy release from this entrance channel to the excited state is not so high, right? So the energy of the photon in the radiative charge transfer is not so large, and it also makes the process relatively slow. So we did the calculation and found that typically you should expect at least 1,000 collisions between the ytterbium ion and lithium atoms before charge transfer happened, what made our experimental colleagues more happy, and they could continue. Anyway, they would probably continue because they got money and they started the experiment, but the prospects were much better. So they finished the experiment. So this is the plot of the scheme of the experiment. Of course, I'm not experimentalist, so maybe I will skip. But the most important is that in the center, in the Paul trap, there is the single ion surrounded by cold atoms. And here, the cold atoms can be moved by controlling the mirror, and the atoms are shifted. So the ion is in the center, the atoms can be shifted to have overlap or to avoid. And of course, we have full quantum control over the hyperfine states, electronic states of both ion and the atom. And now, in the first experiments, they look at the charge dynamics to confirm that really many collisions can happen before some charge transfer happen. And experiment confirmed this, that in fact, for the ground state atoms, this process is very, very slow. In fact, it was hard to measure the rates of the collisions because it was so slow, but it was very nice because at least 1,000 collision happens before the charge transfer happen in the ground state. For excited state was much faster, but maybe I will skip this. We did some electronic structure calculation to get some explanation about the differences for different charge transfer in the excited states. Unfortunately, systems including Ethereum are extremely hard for electronic structure calculations. So this picture, although there are many curves here, it's absolutely simplified and not complete. So we only somehow could make some hand waving arguments. But at the end, we find some explanation that in fact the nature of the surrounding threshold is the most important for the rates of charge transfer in excited state. So then, knowing that we have enough time for realizing the experiments, the experimental colleagues look at the spin dynamics. So now, being in the ground state, different hyperfine states of the Ethereum ion could be populated, and by repeating these experiments for many different initial states, they could measure the evolution of the population of the states in the time, and in this way get the rates for the spin exchange collisions between different hyperfine states of the ion and surrounding neutral atoms. And to explain this or to understand, we also did two-body multi-channel quantum scattering calculations. So this is typical for Maris, as Paul or Jose or other people use. And we did these calculations, and somehow still, because the Ethereum is very heavy atom, so we were not able, and probably will not be able in the near future, to get potential energy curves accurate enough to predict the scattering lengths purely ab initio. So scattering lengths in all my calculations for ion atom systems are always 3 parameters that we have to fit to some observables. So here we did this analysis. So we did the few calculations, and what was initially a bit surprising for us, that although the temperatures here were still quite high because the collision energy were around 1 millikelvin, we could see that depending on the combination of the singlet and triplet scattering length, the spin exchange rates were very different, right? So somehow you could see some coherence effects at high temperatures, although let's say 20 partial waves or more contributes to collisions in these temperatures. Later, our colleagues, Robin Cotte and separately Timur Cherbul, they found that in fact, they called it spin locking mechanism, that for some systems where when some inelastic process with small release of energy happens, you can have somehow you can see the effects of interference already still at relatively high temperature when many partial waves contribute. And recently also Roy Ozeri did some measurements, and I think we see some quantum features in this many partial wave regime. So here we didn't unfortunately push too much this, but we have seen this phase locking mechanism. But okay, knowing that we now have the spin under control, charge under control, the quest was to go to S-wave regime, because I mean this was the challenge for the last 20 years. And I mean here the experiment is very simple. You just take your single ion, you cool it as good as you can with lasers, and then immerse it in the ultra-cold lithium atoms and wait, right? So this is how the temperature of the single ion in the Paul trap immersed into cold lithium atoms, ferment lithium atoms, looks like after waiting up to one second. And you can see at the beginning, the experiment starts with the ion at 600 microkelvins and very cold, ultra-cold lithium atoms at 2 microkelvins. And we finish, I mean, our experimental colleagues in Amsterdam finish with temperature 100 microkelvin. So it means that there is factor of 6 reduction of the temperature. Maybe it's not impressive yet, but still it's much below what they could do with the lasers. And also that it's possible to explain somehow this kind of cooling rate, because if we make the simulation assuming that there is no micromotion, so this would be the dashed line. So then at the end, without micromotion, we should get exactly 2 microkelvins, because we should have thermalization, and this is what classical simulation predict. Then if micromotion is included in semi-classical calculations, then this next dashed line is obtained, what is a bit below, and then the final black curve here is a fit, but also it can be somehow this calculation with the micromotion included, corrected by the heating measured experiment added, and then the agreement is quite good. And now a very important part of the story is that we can ask, what is the collision energy in the center of mass of colliding heavy ion with light atoms. So this is somehow high school or even before math, right? So that you can ask what is the collision energy, and relative collision energy in this kind of system is heavily dominated by the kinetic energy of the atom, right? Because the coefficient standing here is much, much larger than here. In the case of the lithium ytterbium, the mass ratio is very high, and like 1/24 or something like this, right? And it means that the collision energy will be dominated by lithium, right? And we have very cold lithium, and our ytterbium ion is not yet so cold. But now when we make this calculation, we see that at the end, and we have the kinetic energy somehow summation here, right? The different contributions, and then transform it to the collision energy. So this is the relative energy in the center of mass, and you can see that at the end, the ion energy contributes only 6.6 microkelvin, and then the total collision energy for this best scenario, the most optimized in the experiment, was 10 microkelvin. So it means that in the best scenario in this experiment, after cooling, buffer gas cooling with the cold lithium, temperature around 10 microkelvins could be achieved. And this 10 microkelvin is exactly the height of the P-wave barrier for ytterbium ion plus lithium system. So it means that it should be cold enough to see some quantum interference or resonance effects. And this was in the next step. So in the experiment, they decided, okay, they start from 10 microkelvin, and then they can heat it parametrically and observe some dependence, right? If there would be no quantum effects in the classical regime, this point should be just straight line, right? But there is some dependence, and we did our scattering calculations to explain this, and the red curve is the effect of fitting our model to the points, because we had still two free parameters, singlet and triplet scattering length, right? I mean, you can think that maybe this agreement is not perfect because the error bars are large, but if I would plot, I should plot maybe here different curves for different scattering lengths, this curve can be really crazy. So this dependence can be much, much, much different. So at the end, we were able for the first time also to fit scattering lengths for ion atom collision. But like here, you should be also very careful with telling about scattering lengths, because in our scattering model, we didn't include the micromotion and we didn't include the trap, right? So there were many approximations. So in fact, this should be treated as kind of effective scattering lengths that are present in the system where all these effects are included, right? Okay, and in fact, this kind of dependence here is the first measurement of quantum of shape resonances, of quantum resonances in ion atom collisions, right? We can assign P, G, and so on shape resonances. Okay, so in this way, in 2020, this can be updated plot. In the meantime, there were some other experiments, some other techniques, but still, this was the first setup where the quantum regime or the edge of the quantum regime was achieved. So now, I mean, once you go to the collision energy where you see some shape resonances, some quantum effects, I mean, next natural step is to go for quantum control, to have Feshbach resonances and to control this system. And maybe by controlling the collisions, you can even optimize the cooling process and make it colder and better for other applications. So now, if we look how the two-body elastic rate coefficients looks like for different temperatures, you can see that, of course, at high temperatures, at temperature of 1 millikelvin for this ytterbium ion plus lithium system, there is no dependence on the magnetic field. Thermal averaging, many partial waves contributes. You cannot hope for any quantum effects. But if you are at the 10 microkelvin, what is the height of the P-wave barrier, some resonances can survive. Of course, if you could go to much lower temperatures, then Feshbach resonances would be much, much more pronounced. So our experimental colleagues in Amsterdam continue looking at these systems, but in the meantime, an experimental group in Freiburg of Tobias Schatz also work on very similar system where they have barium ion instead of ytterbium, what is not much different, and the same fermionic lithium atoms around. There were many differences probably in experimental setup that I cannot follow, but let's say from my naive perspective, the difference was that here the ion was moved. Like in the first experiment, the atoms were moved and ion was in the center. Here, by applying the offset electric field, the ion was shifted, whereas the atoms were in the center. And somehow following the same procedure as in Amsterdam, so using buffer gas cooling, preparing the ion, cooling it to the lowest possible temperature, putting to the cold gas, waiting some time for equilibration, and having the ion as cold as possible, they started observing the survival probability rate, right? So in this plot, the experimental group plotted what is the probability of the ion surviving the some time, let's say 100 to 300 milliseconds in the ultra-cold lithium gas. And as you can see, for some particular values of the magnetic field, there were some dips, right? And these dips could be associated with Feshbach resonances, right? Here, the collisions were between the mixture of the barium spin states, so the spin of the barium was not controlled, whereas the gas of the lithium atoms could be prepared in different hyperfine state. In this particular case, the first excited lithium hyperfine state was used. And again, the quest was, can we explain these features by doing two-body quantum scattering calculations? So here we presented that we could, in fact, assign some spectrum for this initial measurement of this around 10 resonances, right? I will go to this in a moment back. But then, of course, I mean, to confirm that really these are the Feshbach resonances, and we really have the two-body and three-body physics as we expect, right? Because this three-body physics that is responsible for the losses should be the process of mostly of the formation of the weakly bound molecular ions, right? And the kinetic energy released in this kind of process is responsible for heating the ion. And once the ion is heated, then we see it as the ion loss, right? And then in the experiment, to see that really this is the free body process, they modify the density, and this is the plot showing the dependence of the ion loss rate as a function of atomic density. As expected, this curve has a behavior as second power of the density, what confirms that really the free body process, two neutral atoms and lithium and ion are involved, right? And on the other hand, in the other experiment, I mean, with the same setup, they went to one of the resonances, but at much lower density. So the density in this experiment was around here. So where the free body processes were very slow. And then once the free body processes are very slow, you should see the enhancement of the two-body cooling rate, right? And this is what exactly is seen here. So by preparing the ion in the standard pole trap, then transferring to the optical trap where the lifetime is much shorter, if the cooling process is better, then the ions survive much longer in the dipole trap. And this is this peak exactly kind of following the position of the Feshbach resonance, right? So as I mentioned, we did the full assignment initially, assuming that second order spin orbit coupling is perturbative, right? Because there were a few free parameters. There are singlet and triplet scattering bands as free parameters, but also the second order spin orbit coupling, which we could calculate, should be free parameters that you will see in a moment. So at the end, unfortunately, or fortunately, because it's more work to be done, this is not perturbative regime. The second order spin orbit coupling here is extremely large. And the reason for this large spin orbit coupling is the crossing of our entrance channel with this high excited triplet state, right? So the coupling between this state and this state is responsible for extremely large second order spin orbit coupling, which in fact is the spin-spin interaction, which is responsible for spin non-conserving processes here. And this can be extremely huge. And although we are able to predict the potential energy curves and the coupling between them is unable well, because we are far from perturbative regime, in fact, the exact value of the second order spin orbit coupling will depend on the exact position of this close by vibrational state in the triplet pi potential. And of course, our ab initio potential are not accurate enough to predict exactly this energy difference. So this is our free parameter. So at the end, we have one additional free parameter that is kind of the position of the close by vibrational state in the excited triplet pi state. That is the main source of the short range spin non-conserving coupling. And we are proceeding with trying to explain this because, as I mentioned, it's very challenging. But at the same time, in experiment, measurements were realized for other spin channels. And then we also found the problem that not all predicted resonances were observed, right? And then there can be some features related to the ways how they are measured in experiment. So this is why we also needed free body calculations to see if, depending on the nature of the resonance, we can have, for example, different rates or different population of different bound states. So now also in my group, in close collaboration with Jose, we run free body calculation to understand better the processes here. And maybe one important thing is that for this kind of free body recombination, we can have two possible exit channels. Either weakly bound molecular ions are produced or weakly bound molecules. And as you can see, there is completely different scale of energies. For the weakly bound lithium neutral dimer, there are just few bound states below the threshold, whereas for the ionic molecule, because of the long-range nature of ion-atom interaction, the density of states is much larger. So there can be different energy scales, different length scales to be understood and included in our model. So to sum up, we did theoretical guidance and explanation for the observation of collisions between different ions with lithium, fermionic lithium atoms. We looked and understand the ion spin dynamics. We helped and collaborated closely with experimental group in Amsterdam to realize buffer gas cooling of the single ion to the quantum regime for the first time, to observe and explain the shape resonances for the first time in this kind of system. And finally, last year, first observation of Feshbach resonances in this kind of systems. So I prepared some list of next steps. Maybe I can skip and just thanks for your attention. And here, the most important people that were responsible for our calculation was my PhD student, Darek Wiater, who did initial calculation for ytterbium, ion plus lithium. Now Jacek Gembala is running free body calculation together with Jose, and Martyna Agata Wojciechowska, master student, very talented master student, is also responsible for explaining this huge spin orbit coupling. So thank you for attention, and
thank you for the nice talk. Questions? Yes, please.
Hey, Michal, can you come back to the lithium beryllium, right, system? So yeah, this one. So barium, right? So here you assign the resonances, right? But
yes.
It's certain, but in the table there were some D wave resonances and some
yes.
that was what does this mean? The number?
Yes. So the point is that somehow, I mean, I don't want to put the numbers because at the end, this is like this model that we presented, as we described, was assuming that the second order spin orbit coupling should be perturbative, and the perturbative regime should mean that, for example, S-wave resonances are not much affected because they are not affected in the first order perturbation theory. So in our model, in our first model that we did, there were like three parameters, right? Singlet and triplet scattering length and the strength of the spin orbit coupling, right? And by doing this, we were able to somehow fit these three parameters and reproduce this spectrum in that kind of accuracy typical for reproducing neutral systems, right? But I mean, there was this very important underlying assumption that there is perturbative second order spin orbit coupling. But after several more months of analyzing this, we realized that in fact this spin orbit coupling is huge, right? So it's extremely large. So it's far from perturbative regime. So it means that this assignment may be to correct it. This is why I don't want to put the other numbers because they are not final yet.
So these numbers associated with the S-wave resonances?
Yeah, yes, these are the numbers for S-wave resonances, and for others we also had. I mean, the agreement was relatively very similar. Their agreement was very similar, but I just don't want to put the numbers that most probably can change or can be not the final, right? So this is the assignment. I mean, it works quite well. This is also why we need the other studies like free body calculation and so on to be sure that we really understand it, because it seems
another short question regarding the micromotion. A micromotion that you've got. So in this experiment, the micromotion was actually cancelled, right? Because they transferred the.
It was small. It was. I mean, it was small. But the micromotion is limited to as much as possible. Yes.
Yeah, but this was transferred into the optical trap. Am I correct?
So these experiments were still in the pole trap, right? So there was dipole trap was only used for this one particular experiment at the low density. And this is why we see the enhancement of surviving the ion in the dipole trap, which the lifetime of the ion is the dipole trap is much smaller. So this is like, if we make the cooling more efficient, we see significant enhancement, yes? And of course, this is absolutely natural step for all these experiments to go with the ion to the dipole trap, because then you don't need to care about micromotion. And then, of course, for any ion or any ion atom combination, you could go to the quantum regime. But of course, it's challenging to trap the ion in the very shallow optical trap when the ion is very sensitive to all possible electric field noise and so on. Yes?
Please.
Michal, thanks very much for the nice talk. So at the very end of your talk, you talked about three-body recombination.
Yes.
And you mentioned the production of Li2, lithium-2.
Yes.
Now, in our experiments, when we also worked together with Chris Green, years ago, we did this, but just rubidium and rubidium plus. And what we found is that the production of the neutral molecules is completely negligible compared to the charged one. So I'm now interested to see, are there special resonances that you see, or what are your findings?
No, so this is like what we investigate. So I think that absolutely, we assume that this tunnel is probably dominating, but I mean, because we are now much closer to the quantum regime, so maybe they can be part. But I mean, as you can see from here, right, the overlap, just even the overlap, this kind of bound states for the charged system will be much longer range. So the overlap with the initial colliding atoms will be much better. So of course, it's absolutely expected that the formation of the neutrals will be much smaller. But I mean, it can happen that if there is some bound state close to the threshold or something like this. So of course, at the moment, we don't yet have, I don't know if Jacek already analyzed more carefully the plots that I presented, these plots, because there are some curves, some rates, but
you don't have calculations yet that where we could see some.
Yeah, I mean, I don't know the numbers because there are just very fresh plots from this week.
Okay.
But I mean, the point is, yeah. So we want to check. I mean, most probably it's like it will agree. Most probably it will agree with the classical or semi-classical simulations, right? But I mean, once you will be really cold, I mean, the quantum regime, then I can imagine somehow resonantly enhancing, for example, in some particular scenario, formation of neutral. But it's absolutely hypothetical. There is no yet any clue, and most probably, and in most of the cases, and this is like most typical what is going on in experiment. But yeah, we want to learn more about this.
Yeah, I have a question that goes a little bit in the direction of universality, but sort of trying to come from it from the angle of, you said you have strong spin-orbit coupling.
Yes.
So can you view this as an opportunity to actually make a connection to what's going on in nuclear systems, right? So there, typically you wouldn't have sort of a nice single channel or simple single channel calculation or situation, but you really have coupling between different channels. And so could the atom ion or sort of a 3-body, 4-body system there serve sort of as a model to see and develop connections to nuclear systems?
Yes, this is hard to tell for me, but I mean, one thing that we already learned, that this second order spin orbit coupling is a short range effect here, right? So it means that because we treated it on different ways, we have ab initio values and somehow the different feeds, but at the end it's really short range effect. So it's the shape of this kind of coupling term really is not important. It's important like somehow it's effective coupling. But it can be true because I mean here we have this crossing of the potential is not present in alkali atoms. So this is why this second order spin orbit coupling here is stronger than in cesium or in fact any other neutral system that we know. So of course this may be kind of closer to nuclear systems, but probably I cannot comment too much more about this. Yes.
Other questions? Yes.
Yeah, so do you have a feeling for how the collisions would affect the phonon modes of the ion?
Could you repeat?
So do you have a feeling for how, so say that you have 2 ions and you want to run your quantum simulator. Do you have a feeling if the phonon modes are affected by the collisions, or would you have to shut off your cooling collisions and then run your simulator?
Yes, so I think that here there was only single ion, but of course this is something that could be very much interested, I think, as was or investigated by, I think, Georg recently published some results. I think that still at the moment the systems are probably too hot this kind of correction due to the coupling of the ions due to the mode of the cold gas around would be relatively weak. But of course, what we try to do, or what we analyze and what the experimental group in Freiburg try to do is to see some effect, maybe some modification of the effective mass of the ion in the gas, right? So this is something that they try to follow, right? But it's in fact quite hard to estimate if what would be really this effect, right? And I think that
you mean see the effect in the quantum simulation results, or from the effective interactions?
Yes. So the point is that the experiment can try to follow and measure if they can see the different effective mass, and we also try to with Krzysiek Jachimski in Warsaw to do some estimates of what would be the effective mass for this kind of setup. But I think that the answers are not very conclusive yet.
Thanks.
Okay, there are further questions? Yes.
I just want to follow up on this free body. Do you expect the free body loss to be more severe for the atom ion systems as compared to the neutral systems? Because the range of the interaction is longer and it's a very strong interaction. So do you think it should be worse, right? Or what?
Yes, I think that this is what we expect, but at the same time, like this is why the experimental groups, they selected fermionic atoms, right? So in this, the other thing is that our free body calculation at the moment are for bosonic ones, but we want to do the machinery and to understand it better. But I mean, experimentally selected fermionic to somehow reduce as possible the free body losses, assuming that there is some reduction. At the end, I mean, we don't see looking at the rates the rates in experiments, there is no visible difference between the free body recombination rates between bosonic neutral systems and here the ion and two fermions. So somehow maybe the experiment is still too hot to see somehow suppression due to the fermionic symmetry. But yes, but there is this is I think the presence. So we free body calculation we started, yes, but it's like there are many stages. Like we started from ion and to bosons, right? Then the next stage, I don't know what will be next stage, is either including hyperfine or going to two fermions and trying to include other effects. But because until now there was really no. Classical, the classical there are. In classical regime it's quite well understood, yes. So of course. I mean, our quantum free body calculation are very fresh in the sense. Yes, I think that yes, I think that the dependence was of course it's what is challenging experiments to know very well density, but I think that orders of magnitude agreed. Yes, I think that there was nothing surprising there. And most probably the experiment is in the regime where absolutely your calculations works, right? So we are still probably far away or a bit away from seeing so our quantum calculations are somehow going into the future rather than trying to explain, except somehow the effect, for example, that we don't see some resonance, and then really we would like to somehow see different branching ratios and to understand because this is maybe important that how the Feshbach resonances are measured, because if the released energy due to the free body recombination is too small, then the loss of the ion would be not visible in the spectrum, right? So this may be the reason why some resonances in other channels are not visible, because if, for example, you have most of the free body recombination going to some very weakly bound state with small energy release, this kind of energy will be not resolved in the spectrum, right? So yes.
Okay, Michal, thanks for the update and all the progress in atom stuff. But one question, I'd like to ask an experimental question, so to give you a perspective on this. So you mentioned at the end the use of the dipole trap. How would you see the prospects for using dipole trapping of ions in relation to ion atom work? How that might develop? I know the traditional ion trap technology is very well developed, but the dipole trapping is much harder. So what's your perspective on that?
I mean, I think that several groups is pushing this, right? So I mean, it's maybe surprising, right? That I think that the ion on their own were trapped already 10 years ago, I think, for the first time in the optical trap, right? But I think that yeah, so this is what they push, or I mean, both Florence and because in Florence they also have barium lithium, and Florence and Freiburg what they I think hope to have some kind of combination of static electric field and optical trap. So just to avoid micromotion, but still somehow supporting the partially with the static electric field. And of course, I mean, the problem is that you have to initiate the system, you have to start from something else, right? It will be rather infeasible to just take the ion and start with the dipole trap. So there will always be the Paul trap stage, and then kind of transfer to the optical trap. So I mean, this is what I hope, because I mean, if you want to see all this more quantum behaviors, if you want to see few body physics in the systems, or polaronic physics, or bipolaronic, I mean, it has to be in the dipole trap at the end. What will be very challenging, but hopefully it will happen. So this is also why, I mean, why I think that if theoreticians here predict more interesting physics, it will convince experimentalists to push to continue this direction.
I think we should move on, and let's thank the speaker once again.